Hello, my name is Kevin Bittner, and I will be talking about the theory of the viscosity lab, whose objective is to measure the viscosity of a fluid using a Brookfield viscometer and a falling sphere viscometer, and to compare those values to also literature values.
Hi, I'm Andrew Cressman, and I will be discussing how to use the falling sphere viscometer. I'm not actually in this lab.
Hello, my name is David Bowl, and I'll be talking about the PPE for this experiment, as well as how to use the Brookfield viscometer. Before beginning the laboratory experiment, it's important to make sure that we're wearing the proper personal protective equipment. As you can see, I'm wearing closed-toed shoes, long pants, and long sleeves. Before I enter the lab, I will put on safety glasses. And then, as I enter the lab, I will write my name on the sign-in sheet. Then, before I begin the experiment, I will grab nitrile gloves. It's important to wear gloves for this experiment because our hands will come into contact with the liquid.
In this part of the experiment, we'll be using the falling sphere viscometer. As you can see, we have 3 different cylinders. Each are filled with different liquids, and you'll be assigned which liquid to find the viscosity for. It is very important to keep safety in mind while doing the experiment, so make sure you have your hands on the railings while you're going up and down the stairs so as to prevent you breaking something. Also, if any spillage does occur, make sure you mop it up immediately and put out the appropriate signage. In using the falling sphere viscometer, you will be choosing 9 unique spheres. It is important to keep in mind while choosing these 9 spheres which ones will tell a good story with the results you are dealing with for your design of experiment. After you have chosen your 9, record the diameter of each and also the mass so that you can determine the density, and this value will be used in further calculations. Okay. Before you do any experiment, it's important to make sure that you have a beautiful TA to watch over you to make sure that everything is going swimmingly. So in this part of the experiment, we have our sphere, and it is very important that you wet the sphere before you let it go. So I will demonstrate as such. Also, it is important to remember to keep the sphere as close to the middle of the cylinder as possible so you can reduce any effects that the boundary wall might have while falling. Make sure to randomize the order of your trials. After you have dropped the sphere, have a partner record with a stopwatch the time it takes for the sphere to come from the start line to the stop line. It is also important to note that this initial falling period is there to ensure that the sphere has reached its terminal velocity before you start taking data. After you have completed all 45 of your runs, make sure you check the Reynolds number for each sphere to ensure that the Reynolds number is less than 2. If you have a Reynolds number greater than 2, you need to choose another ball, and hopefully those runs will yield a Reynolds number less than 2. So after everything is complete, you can use these wires to fish out your spent balls and clean them up and make your TA.
This is a special piece of equipment called a Brookfield viscometer. It's used specifically to measure the viscosities of liquids. Before using the viscometer, check that the bubble in the back is within the circle. It's important that the viscometer be level to get accurate readings. The next thing we'll do is auto-zero the viscometer. To auto-zero the viscometer, first we turn on the power switch. Then we make sure that this dial over here is set to 12 RPM. Next, we will turn the motor on, and then we will push the auto zero button. After the display stops flashing, the viscometer has been zeroed. Now it's time to choose a spindle and start making measurements. There are several different spindles to choose from. be sure to explain why you chose each spindle in your design of experiment. Another aspect of the design of experiment for the Brookfield viscometer is what rotation speed you use. When putting the spindle on the viscometer, be very careful because there are pinching hazards present. Be sure to secure the top piece with one hand and screw the spindle on with the other.
Make sure to randomize the order of your trials.
After the spindle is securely attached to the viscometer, you'll need to enter the spindle number into the data pad. To find out what number your spindle is, you'll use the data book that's in the lab. In this example, we've used spindle LV2, so that means we must enter 62 into the viscometer. To do that, we will first push the SPDL button, then enter the number, and then choose the units. In this lab, we will use centipoise. Lower the spindle into your beaker of liquid by using the knob in the back. It's important that after you lower the spindle into the liquid, you make sure that there are no bubbles caught beneath the spindle, as this will affect the viscometer reading. After you've ensured that there's no bubbles beneath the spindle, you turn the motor on and then wait for the reading to stabilize. After the reading is stabilized, you can record the viscosity, turn the motor off, and raise the viscometer back out of the beaker using the knob in the back. And as always, if you spill any liquid, use the mop to wipe it up and place the appropriate sign.
So I'm here to talk about the theory behind the viscosity lab. We've already discussed the Brookfield viscometer and the falling sphere viscometer, and as we mentioned before, the Brookfield viscometer directly measures the viscosity of the fluid, so there are no calculations behind that. We just took our trials and we averaged them together to get the viscosity of our fluid. For the falling sphere viscometer, though, we actually have to calculate the viscosity of the fluid. And we do so by applying a force balance on the falling sphere, where we have the gravitational forces acting on the sphere as it falls, equaling the buoyant force that's opposing its motion, that's caused by the fluid displaced by the sphere, and the forces due to the motion of the fluid as the sphere falls. So we can take this equation and we can rearrange it to solve for the viscosity of the fluid, and we end up with this equation where d equals the diameter of the sphere that's falling, rho subscript s is the density of the solid sphere, rho subscript L is the density of the liquid through which the sphere is falling, g is our gravitational constant, and v sub t is the terminal velocity of the sphere as it falls through the viscometer. So in order for us to be able to use this equation for the viscosity of the fluid, we need to make several assumptions about our experiment. The first one is that as the sphere falls, we are having a Reynolds number that is less than 2. Since the Reynolds number is a proportion of inertial forces to viscous forces, this assures that our viscous forces are some of the more dominant forces in our system. Our second assumption is that the sphere is falling at terminal velocity, meaning that our forces due to the motion of the fluid are staying constant. This can be achieved by measuring a starting and stopping time farther down in the tube rather than just at the initial drop site. Our third assumption is that the diameter of the tank is at least 10 times greater than the diameter of the sphere. This ensures that there are no boundary conditions affecting the sphere as it falls. You will want to make sure you measure the diameter of the tank so you know what diameter spheres you can use during your experiment. And then our fourth assumption is that the fluid is a Newtonian fluid,